So we are moving forward with our lecture, and today's lecture will be on drawing Lewis structures. A quick recap of the first lecture where we were introduced to bonding generally, and we saw that the electrons in the valence shell are the only ones that participate in any chemical bonding. And when they participate in bonding, they do so that the atom will be able to attain an octet. And the atoms, the electrons attain octets either by sharing electrons, gaining electrons, or losing electrons. And we found out that ionic or electrovalent bonding involves the transfer of electrons from one atom or the other to the other, and usually from the electropositive element to the electronegative element to attain an octet nature or of the next noble gas. And the lecture on Wednesday, we looked at covalent bonding, which has to do with sharing of electrons. And when the electrons are shared between atoms, it is also for the same purpose that they may attain the octet configuration. And towards the end of the lecture, we saw the second type of covalent bonding, which is dative bonding, whereby the two atoms that are bonded together, one of them gives the pair of electron, while the other one does not have any electron, as in the case of ammonium ion. We were able to also differentiate between a bonded electron pair and non-bonding electron pair, which are also called lone pair of electron. We look at valency, bond length, bond order. So today we are moving forward and we're drawing Lewis structures. So what are the things we're going to be discussing in this? We're going to be drawing Lewis structures by still following this octet rule. Remember that we talked about when you're drawing elements, you only put the dots of the number of electrons that are in the valence shell. For example, sodium, when you draw the Lewis structure of sodium, you don't put all the 11 electrons on it. Sodium has 11 electrons, but only one valence electron. So just put one dot, and that tells you that that is sodium. We also want to look at how to draw Lewis structures with single bond, double bond, or triple bond. We will equally look at whenever there are sometimes they have isomers, and how do we draw their structures? Then we look at resonance structures, how to calculate formal charges, and we are also looking at the violations of the octet rule. Remember that for every rule, there is always an exception. So that octet rule has some exceptions, and the exceptions are sometimes your molecules may have odd number of electrons, and you know that octet is an even number. So when you have odd number of electrons, definitely you can't form an octet. Some molecules have electron deficiency. They can never form octets. They have fewer than 8 electrons between them. So there will be electron deficiency in such molecules. Sometimes some molecules are even capable of forming more than 4 bonds. So these are the exceptions to the octet rule that we'll be seeing in the course of this lecture. So the Lewis, you can see that we call it Lewis structure, is with this name, it was named after the person that proposed this. And in 1916, more than 100 years ago, G.N. Lewis proposed that atoms combine in order to achieve a more stable electron configuration. And that is where we form the octets, because you know that on the periodic table, the most stable elements are the noble gases that have 8 valence electrons. So now, the maximum stability results when an atom is isoelectronic with a noble gas. So we talked about when you have, for example, sodium is 281, but you know that neon is 28. So when sodium loses 1 electron, it attains the configuration of neon, which is 28, and that will be, it is going to be Na plus. Similarly for fluorine, fluorine has 287 and 27. So when it gains 1 electron, it also becomes 28, and that will be the configuration of the next noble gas, which is neon. So at any time there is a bond between 2 atoms, 2 electrons are usually involved. And when we're talking about this Lewis structure, we are not talking about ionic bonding. We are focusing now on covalent bonding, whereby electrons are shared between 2 atoms. So when a covalent bond is formed, a single covalent bond will have an electron pair containing 2 electrons. When a double covalent bond is formed, now 4 electrons are involved. When a triple covalent bond is formed, 6 electrons, 3 pairs of electrons and 6 electrons are involved. So in drawing covalent Lewis structures, we use what we call the dots. And that dot, like I said, is only applicable to the valence electrons. So the dots, for example, sodium will have 1 dot. So let me ask you now, for calcium, how many dots will calcium have? How many dots will calcium have? You can type in the chat box. How many dots will calcium have in the Lewis structure? Calcium. Nobody's in the chat room. Calcium, yes, it will have two electrons because it has 2 valence. So when you draw calcium, just put 2 dots, and that will tell you that that is the valence electron. Thank you. So we use the periodic table to determine the number of dots. So you know that group 1 elements have 1 valence electron. So all sodium, lithium, potassium will have 1 dot. Calcium and magnesium and group 2, they will have 2 dots. Beryllium will have 3, boron will have 3, carbon will have 4, nitrogen will have 5, oxygen will have 6, fluorine will have 7, neon will have 8. So each of them has the group they belong to on the periodic table dictates the number of dots that they have. So it works very well for the first full row on the periodic table. But the second full row, it has some restrictions, and that is when we start talking about the exception to the rule. So now let's look at this. This is just what I've said before. So the number of valence electrons are represented by dots. Somebody is asking, how do we find valency of transition elements? Remember that transition elements are metallic, and covalent bond is usually between non-metals. So we can't talk of this for covalent bond. We can't talk about transition elements because transition elements are metallic. So we are only talking more about we're talking now about non-metals. So that is why we'll be focusing more on non-metals. So looking at this now, you can see group 1, you have 1 dot. Group 2 will have 2 dots. And remember, the 2 dots will not be placed together. You put them singly before you start pairing them up. Group 3 will have 3, boron and aluminum, you can see. Group 4, these are just for the first 20 elements. Carbon will have 4, silicon will have 4. Nitrogen, you notice that you click the 5, but 1 will be paired. Similarly with phosphorus. Oxygen has 6, 2 will be paired, 2 others will be single. See that fluorine has 7 and neon has 8 and argon. So that is so your valence number is the same thing as the group they belong to on the periodic table. I hope you understand that. So the Lewis structure now. So the Lewis structure and the how we get that. The Lewis dot line representations of atoms and molecules. So we can, just like we can use the Lewis structure for atoms, we can also use it for molecules. So in the electrons of an atom, we have 2 types of electrons, which I have said before. We have the core electrons and the valence electrons. Like sodium now, it has a configuration of 2, 8, 1. So 2 and 8 are the core electrons, while the valence electron is the one that is in the valence shell. So the number of valence electrons is equal to the group number of the elements for the representative valence, which you have seen before. So for atoms, the first 4 dots are displayed around the 4 sites, as you can see before the previous slide. So for the first 4 groups, you see the 4, they are displayed singly. And if there are more than 4 electrons, the dots are paired with those already present until an octet is achieved. So you first do it for nitrogen, for example, you put it has 5, just 1, 2, 3, 4, then the 5th one will be paired. For oxygen, 1, 2, 3, 4, then you now pair 5 and 6. So you first do them singly before you pair them for those that have more than 4 valence electrons. So ionic compounds are produced by the complete transfer of an electron from one atom to other. But like we're saying, for these Lewis compounds, we're going to be looking at covalent compounds, where one or more pairs of electrons are shared between two atoms. So covalent bonding and Lewis structures. The covalent bonds that are formed by the sharing of electrons between atoms, and these Lewis structures are only found in molecules that possess covalent bonds. So the bedrock for writing Lewis structures for the first full rule of the periodic table is the octet rule, whereby you have your carbon, nitrogen, and oxygen. So carbon, nitrogen, and oxygen are usually, they are surrounded by 8 valence electrons. So you can see now that carbon, in our previous slides, carbon, nitrogen, and oxygen, you can see the number of electrons that surround them. So we use that. But for hydrogen, hydrogen cannot form an octet. Hydrogen can only form a duplet. So you can't make hydrogen 8. Hydrogen can only be 2, same as lithium can only be 2. So for hydrogen atoms, the duplet rule is applied. Hydrogen atoms are usually surrounded by 2 valence electrons, while your carbon, nitrogen, oxygen, fluorine will be surrounded by 8 valence electrons. So in writing Lewis structures for compounds, these are the steps that we're going to follow. You first get the skeletal structure of the polyatomic ion or molecule. And we don't only write it for molecules, we also write it for ions. Like maybe you have your SO42 minus, we can draw the Lewis structure. So the skeletal structure of the atom, of the ion or the molecule indicates the order in which the atoms are attached to one to another. Let's say we have water, for example, H2O. If somebody can say HHO, another person can say OHH, and somebody can say HOH. But there must be an order in which the atoms are attached one to the other. So this is the Lewis structure, helps us to know the arrangement so that we have the proper one. Just like if you want to draw a human being, for example, you draw a human being. Let me try to draw a human being. You know that this is the skeletal structure of a human being. You have the head, you have the body. Maybe it's a boy, a male. You draw the body, you put the legs. He's wearing a short. This is the skeletal. Trying to draw a skeletal structure. So this is the hand. This is the other hand. This is the leg, and this is the leg. So whoever sees this knows that this is a human being. But I know that the leg, the feet must be connected to the leg connected to the short, and the top, and the hand, and the head. It will be hard for somebody to draw a human being like this and put this. Draw a human being and put the head here. I say, after all, this is a human being, the head can be here. You know that this is wrong. Even though all the parts of the body, you now put one leg at the head, put the other, now put the hand, put the second leg. And I say, but all the parts are complete. After all, I'm not missing any parts. But you know that even though all the parts are there, they are not correctly linked. So that's the same thing the Lewis structure helps us. So as in, you can write water. We know water has 2 hydrogen atoms and 1 oxygen atom. So we know that water can be drawn this way. You can draw water this way. Somebody can say, okay, no, my own water will be like this. H. The hydrogen will link hydrogen before oxygen is linked. Somebody can say, this is my water. After all, I didn't lose any atom, H2O. Another person, no, I'm going to write my oxygen first and put my hydrogen to follow. So whoever does this, so doing this now, there'll be confusion because in writing any of these 3 structures, the 2 atoms are present, 2 hydrogen atoms and 1 oxygen atom, 2 hydrogen atoms, 1 oxygen atom, 2 hydrogen atoms, 1 oxygen atom. So to avoid this ambiguity, just like somebody drawing a human being and say the head is there now, I can put the head anywhere. It's the same thing that you're drawing your atom, your molecule, and the atoms are not linked properly. So what helps us to do this linking is the knowledge of the Lewis structure. So when we draw Lewis structure, we'll be able to place the atoms appropriately where they are supposed to be. We'll be able to do that. And in doing that, the first step is that you have to know the central atoms. So the central atoms, so when you have a molecule, the first thing you need to do is to identify what or which are the central atoms and which are the terminal atoms. How do we identify the central atom? A central atom is bonded to two or more atoms in the structure. So when you have an atom, when any atom in the structure is bonded to two or more atoms, that is the central atom. And a terminal atom is an atom that is only bonded to one atom. So when it has only one bond, that's the terminal atom. And when we are writing the skeletal structure, the idea is that every atom must be connected to the rest of the structure by at least one bond. Just like when you draw a human being, the head will not be floating. Every of the parts of the body must link up together. So when we're drawing the skeletal structures also, every of the parts must be linked together. The parts must be linked together. That is what gives us an idea that, okay, we have the complete structure of the atom. So I'll go over it again. There must be at least one central atom and at least two terminal atoms. The central atom is that, how do we identify the central atom? The central atom is that atom that is bonded to two or more atoms in the structure. The terminal atom is only bonded to one other atom. And when we're writing the skeletal structure, every atom must be connected to one another. So we have some rules that also govern this. So how do we know the number of valence electrons or the bond that the atoms will have? So we have different families of elements on the periodic table. The first family we're looking at are the halogens. The halogens, as we know, they are group 7 elements comprising of fluorine, bromine, chlorine, and iodine. They're in group 7. So they have 7 valence electrons. So in sharing, anytime you have any of these, you want to form a bond, you can only form one bond. Why is this so? Because it's only one electron they need more to form an octet. So this one can now be shared by any other atom. So if another atom comes in here, for example, so another atom, let's say we have atom Y. This is an hypothetical atom. It has an electron that it can share with an halogen. So when this happens, the halogen will now be 1, 2, 3, 4, 5, 6, 7, 8. So that is why the only bond that the halogen can form most times is a single bond. Then we have the chalcogens. The chalcogens are group 6 elements: oxygen, sulfur. And as we know, they have 6 valence electrons, and they can often, and you can see of these 6 valence electrons, 2 are already paired. So this one is already paired, and this other one is paired. So oxygen can form 2 bonds, either one way, this way, links up with an element, maybe element Y. That same element Y can come with 1 electron, and come with an element Z, can form 1 bond again. So oxygen can form 2 bonds, that is one bond on either side. That will be 2 bonds. Or oxygen can decide to say, I can form a double bond. Oxygen can form a double bond with an element. Let's assuming that this is not there. Let's clean this off. I can't clean this off now, but assuming this is not there. So oxygen can form 1, 2, 3, 4, 5, 6, 7, 8. So is that oxygen goes this way, having a double bond. So oxygen can have a double bond, as you can see here, or it has 2 single bonds on either side. So that is also the 2 bonds we are talking of for chalcogen, sulfur, and oxygen is either a double bond or 2 single bonds. But in all, oxygen will do this to also attain an octet. And if you look at this, there are 2 valence electrons, 4 electrons there. 1, 2, 3, 4. So you can see it's 1, 2, 3, 4, 5, 6, 7, 8. And here too. 1, 2, 3, 4, 5, 6, 7, 8. So is either oxygen forms a double bond with an element, we'll call this element X, or it comes, maybe it comes Z and Q or Y. So you can form two single bonds or a double bond. So that is how you know the type of bonds the chalcogens can form. Then for nitrogen and phosphorus group 5, they can also form 3 bonds. And as you can see for nitrogen can form a bond this way. You have a nitrogen has 1, 2, 3, 4, 5. So you can form triple bond. So this is still 1, 2, 3, 4, 5, 6, 7, 8. But nitrogen can form in some amino compounds, can have a double bond here and a single bond here. And you have a lone pair of electrons. And this is still 1, 2, 3, 4, 5, 6, 7, 8. Or you could have sometimes, you could have, this could be like this, like this, like this. You have your lone pair 1, 2. So this is still 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen will form 3. Now let's look at carbon or silicon group 4, can form 4 bonds. So carbon can decide to take it this way. We have 1, 2, 3, 4. And as you can see, this is, you can look at the electrons. This is 1, 2, oh dear. Can you hear me? Hello? Can you hear me? Okay, thank you. So let's go back to calcium. I think my internet disconnected me momentarily. So let's look at calcium, carbon and silicon. So look at carbon and silicon. So carbon this way. So carbon can have 4 electrons, 1, I mean 4 bonds, 2, 3, 4. And if you count it, these are the electrons. The carbon has 4 valence electrons originally, 1, 2. Let me annotate with another color. So we have 1, 2, 3, 4. So you can form electron with 4 single bonds. This can be carbon, and that will be an octet. Or you have it, carbon can form a triple bond, as in your ethane, a triple bond, and a single bond. And if you count it also, you're going to have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. Or carbon can also form 2 double bonds. So carbon can also do this. 1, 2, 3, 4. Like in your diene. So you can have 1, so this is 1, 2, 3, 4, 5, 6, 7, 8. Carbon can also have a double bond and 2 single bonds. So in all, carbon cannot have 5 bonds surrounding it. Either 4 single bonds, a triple bond and a triple bond and a single bond, 2 double bonds, or 2 single bonds and 1 double bond. So you can't have carbon that will have, did not be 1, 2, 3. Carbon cannot have this. It's not possible for carbon to be surrounded by 5 bonds. So these are the things, these are the rules that govern our Lewis structure. So once you know this, you will not be, so when you're not drawing your skeletal structure, you won't give more than the necessary number of bonds. So this is a guide to tell us number of bonds that can be formed by these elements. Similarly, hydrogen cannot have more than 1 bond. Hydrogen can only have 1 single bond in hydrogen. You can't have hydrogen hydrogen cannot have double bond. You can't have hydrogen that has connected to 2 ways. No. Hydrogen has only 1 valence electron, and so it can only form 1 bond with any other element that it can join itself with. So these are the rules that will govern what we are talking about. So now, the guidelines in doing this, when compounds are formed they form the octet, they follow the octet rule. And the octet rule says that atoms will share electrons until it is surrounded by 8 valence electrons. Atoms will share electrons until surrounded by 8 valence electrons. So when you are forming, when you're drawing your Lewis structure, every atom in that molecule must have 8 valence electrons, except hydrogen, which we have said before that hydrogen can only form a single bond. Hydrogen can only form a duplet, so you can't make hydrogen an octet. So what are the rules? We call it the valence shell electron pair repulsion, VSEPR, valence shell electron pair repulsion. We get to that later. So now the octet rule works mostly for second period elements. On the periodic table, we have the first period, we have the second period. So the second period, it works well for, by the time you get to the third period on your periodic table, you know that in your phase 112. The third period, where we now have the d orbital. You know, the first period and the second period, your electrons end either the s and p orbitals. That's where the electrons are found. By the time you get to the third period, that's where you now get to the third shell, and that's where you have your d orbital. So there will be some anomalies when you get to the d orbital. So now we'll look at those that follow the rule before we look at the exceptions. So hydrogen will always have 2 electrons. As hydrogen will never have a double bond, because that's only one single valence electron, and that valence electron can be shared with another atom's electron to form a single bond. So for hydrogen, for example, we will never have a double bond. So looking at carbon now, you see that carbon has 4 valence electrons. So carbon so the 4 electrons can come this way, like I've shown you before. So carbon can have 4, it can share either ways, 2, 2. Nitrogen has 3 unpaired electrons, so it can form 3 bonds. Carbon has 4 unpaired electrons, can form 4 bonds, 1, 2, 3, 4. The 4 can be single bond, or 2 double bond, or 1 double bond and 2 single bonds. Nitrogen has 3 unpaired electrons, so these 3 unpaired electrons can form 3 bonds. Oxygen has 2 unpaired electrons, can form just 2 bonds, either a double bond or 2 single bonds. And fluorine has 1 unpaired electron, can only form 1 bond. You can't see a double bond between 2 fluorine atoms or 2 chlorine atoms. And remember, we said in drawing this, we also have what we call the central atom. So hydrogen and fluorine can never be central atoms. The reason why we remember the definition of our central atom is that a central atom is bonded to 2 or more atoms in the structure. And because hydrogen can only have 1 bond, it can't be bonded to 2. Fluorine can only have 1 bond, cannot be bonded to 2. So hydrogen and fluorine are always terminal atoms in the structural formula. You can never see hydrogen or fluorine as a central atom. Our definition then said that a terminal atom is bonded to only 1 other atom. So that means that the hydrogen will always be a terminal atom, because it's only allowed to form 1 single bond, while the central atom can be bonded to 2 or more. So carbon, oxygen can form central atom because they have the capacity to be bonded to any other. So this oxygen can be at the center, or carbon can be a central atom. Nitrogen also can be a central atom, but fluorine, hydrogen can never be central atom. So let's look at the connectivity now. So we have an example. We have CH2ClF. Looking at this now, carbon, hydrogen, chlorine, fluorine. Fluorine has only 1 unpaired, 1 electron that is not paired in the valence shell. Chlorine has 1 electron that is not paired in the valence shell. Hydrogen, each of them has 1 electron. Carbon has 4. So carbon becomes the central atom here. In HNO3, nitrogen is there, can form 3 bonds. So nitrogen can be the central atom. And oxygen can never be, hydrogen would always be a terminal atom linked to this. So nitrogen has only 3. And if you look at it as we were looking at it before, We see here that nitrogen can only form 3 bonds, 3 single bonds, 1, 2, 3. So that is why this hydrogen cannot come in, because if hydrogen comes here, nitrogen will be having 5 valence electrons. Then for carbon, you see carbon also can have 4, it has 4 single electrons, so you can form 4 single bonds. So that is why the other 4 atoms, 2 hydrogen atoms, will be terminal, the 1 chlorine and 1 fluorine. Similarly for nitrogen, it will be central atom, surrounded by the 3 oxygen atoms. And this hydrogen, you can't bring hydrogen here, you have to bring it here. Looking at this now, you have 2 carbon atoms. So these 2 carbon atoms can be central atom. The hydrogen here, the 4 hydrogen atoms will be terminal atoms, and this carbon will have the 2 oxygen. Hydrogen selenide, so selenium is a group 2 element, so selenium can also be a central atom. H2SO4, sulfur 2 can, sulfur is in the same group as carbon, so you can have 4 bonds, and you now surround the others. Oxygen can be in ozone, oxygen is the central atom. So we can see, we'll look at it more. So in general, when there's a single central atom in the molecule, all the molecules we have, the central atom is the first atom in the chemical formula. So you can see that it is a single central atom, it will be the first atom in the chemical formula, NH3, PO43 minus CO2, O3. So this will always be the first atom in the chemical formula. And this can, but there's an exception, except when the first atom in the chemical formula is hydrogen. So like you have H2SO4, hydrogen can never be central atom. In this case now, like in H2SO4, you can't follow this rule and say hydrogen is the central atom because it's the first atom in the chemical formula. So like I said, for every rule, there is always an exception. So and the exception is when hydrogen or fluorine is the first atom in the formula, it will never be the central atom. So now find the central atom. We have a quiz now. So in the chat box, question 1. So in question 1, find the central atom in H2O. Is it hydrogen or oxygen? The central atom in H2O. I said hydrogen can never be central atom. Always listen. Always listen. The rule says that hydrogen, when the first atom in the chemical formula is hydrogen or fluorine, hydrogen can never be central atom. And I've done an example before here, H2SO4. You can say that sulfur is the central atom. Okay, everybody, almost everybody got that. Let's look at the second one, SO3. Which one is the central atom? SO3. Sulfur, correct. Beryllium hydride. Beryllium hydride. Beryllium, okay. PCl3. Phosphorus trichloride. Phosphorus trichloride, okay. Carbonates. Carbonates, carbon and oxygen. Which one will be the central carbon? Iodates. Iodates. Iodine, correct. Thank you very much. So that ends our exercise. So note the following, still note this. Hydrogen atoms are nearly always terminal atoms. Almost all the time, hydrogen atoms are always terminal atoms because they only form 1 bond. They can only form a duplet and can only form 1 bond. So hydrogen is always a terminal atom. In polyatomic molecules, and I'm sure you know what polyatomic means. Polyatomic means you have more than 2 atoms in the molecule. Your polyatomic atoms are examples are what we have done before. All these are polyatomic. You can see they have more than 2 atoms in their molecule. They are all polyatomic. So in polyatomic molecules of ions, the central atoms usually have the lowest electronegativity. The lowest electronegativity is usually made the central atoms, except for hydrogen. We know hydrogen it has very low electronegativity, so we don't count hydrogen. We look at that one. So in polyatomic molecules of ions, The central atoms have the lowest electronegativity. So when you have two atoms that can stand as central atom, the one with the lowest electronegativity will be the central atom. In oxo acids, hydrogen atoms are usually bonded to oxygen atoms. So see in acids, for example, hydrogen is usually bonded to oxygen. So your hydrogen will always be bonded to oxygen. So hydrogen is always bonded. So whenever you have an acid, hydrogen is always bonded to oxygen. With the major exception of carbon compounds in which long chain of carbon atoms are common, polyatomic molecules, usually and ions form compact structures. You don't want it to be, so maybe you have, let me write an example for something of that nature. You don't write, let's say you don't write maybe, let's say for this, let's look at this previous example. I want to use that rule for the previous example. Computers and okay. So you form compact structures. Let's look at this example. I want to illustrate what I mean by that. In this H2SO4, you can see it is a you don't write to H2SO4 and do like this and put sulfur, oxygen, oxygen. Now put it, make it a very long chain and put all your 4 oxygen like this. No, and now put your hydrogen here and put hydrogen, maybe now put hydrogen here. This is too long. The rule says that, what the rule says is that we should make it as compact as possible. So you have to make it a compact structure. You try to make it as compact as possible. That is what the rule states. So the rule says that with the major exception of carbon compounds, where you have long chain hydrocarbon, polyatomic molecules usually form compact structures. So steps for writing Lewis structures. Determine the total. We want to look at how to write Lewis structures now. How to write Lewis structures. So number one, you determine the total number of the valence electrons. You determine the total number of valence electrons. That's the first step. So once you write Lewis structures, you have to pay close attention to this step. So one, determine the total number of valence electrons. So let's look at an example of this N2O4. Nitrogen is in group 5, so and there are 2 atoms of nitrogen. That would be 2 times 5. Oxygen is in group 4, has 4 valence electrons, and there are 4 of them. Oxygen is in group 6, sorry, has 6 valence electrons, and there are 4 of them. That is 4 times 6. So N2O4 has 34 valence electrons in the entire molecule. Let's look at the anion, NO3 minus. Nitrogen is in group 5, 1 atom of nitrogen, so 5 valence electrons. Oxygen is in group 6, 3 atoms of oxygen, so that would be 3 times 6, 18. And because it carries a negative charge means what? It has gained an electron. Anytime you see negative charge, it has gained, like your chloride ion, your chloride ion, fluorine ion, oxygen ion, they will be negatively charged. So anytime you see a negative charge, it means it has gained an electron. That will be +1. So if it is CO2 3 we'll do that later. So when you add this together, that's 24 valence electron. If it is a cation, like your ammonium ion, it means it has gained and it has lost an electron. So it's going to be 5 plus 4 times 1 minus 1. That will be 8 valence electron. So now I want to give you an example of what we do now. So in the chat box, let's do for CO3 2 minus. Let's do H2 SO. So begin to type in your chat box. Total number of valence electrons for CO3 2 minus. Yes, CO. So people are writing 24. Is that correct? Someone is writing 22. Is that correct? So it's 24. Who is that writing 20? 24. So carbon is in has 4 valence electrons. That is 4. Oxygen has 6 valence electrons, and there are 3 of them. 6 times 3, that is 18. And because it has gained 2 electrons, we add 2, and that now gives us 24. So 24 valence electrons. What about H2SO4? So H2SO4, as you can see, is 32. Hydrogen is 2. 1 atom, 1 valence electron, 2 atoms of hydrogen. Sulfur is in group 6. So that will be, and we'll have 1 sulfur atom. And oxygen is also in group 6, and we'll have 4 of them. That's 24. The 24 plus 8, that's the 32. So now you know how to calculate valence electrons, total number of valence electrons. That is how we calculate that. So let's move on. The first step in writing the structure is determine the total number of valence electrons. So now the next rule is that from the chemical formula, determine the atom connectivity for the structure. From the chemical formula, determine the atom connectivity. So I have a formula like, for example, ABN. You already know that A is the central atom, and you have N number of B surrounding it. Like you have NH3. Know that N is the central atom surrounded by 3 hydrogen atoms. NCl3, N is the central atom surrounded by 3 chlorine atoms. NO2, N is the central atom surrounded by 2 oxygen atoms. And remember, always remember that hydrogen and fluorine can never be central atoms. Now, after you so the first step is calculate the total number of valence electrons. The next one is look at the atom connectivity for the structure. Then number 3, you now write the skeletal structure and connect the bonded atoms with an electron pair. So now do the skeletal structure. So for this one, I can do this now for my AB. So for that, I can say that, okay, I've determined that A is the central atom surrounded by, let's say I have AB. Okay, let's look at the main example, NH3. So that nitrogen is the central atom. And remember our rule that says that nitrogen can be surrounded by 3 bonds. This is mine. I'm sorry, I won't do that yet. So I'll just know that nitrogen is my central atom. I'll now put my terminal atoms around it. So hydrogen, 1 hydrogen atom here, another hydrogen atom here, and the 3rd hydrogen atom stays here. So this is just what I need to do. So I will write the skeletal structure, put my central atom at the center, and put the terminal atoms surrounding my central atom. So that is step 2 we have done. And step 3, we now add the dash, the bond, we make the bond formation. So the next one is now place electron pair around the terminal atoms so that each atom has an octet. Assign the remaining electrons as lone pairs around the central atom. So now let's look at a typical example. I don't want us to lose these steps. Determine the total number of valence electrons. Determine the atom connectivity by knowing which one is the central atom, which one is the terminal atom. Then you write the skeletal structure and put your dash in between. You place your electron pair around your terminal atom so that each atom has an octet. Then you assign the remaining electrons. These steps, we'll understand it better when we do an example. So let's look at an example. So this is the step, like I said before, you write you have the molecular formula, you sum the valence electrons, you put the electrons around them, and you get a little structure. So let's use the example that we have on this slide. This slide is running too fast. So let me put, we have NF3. So the first step is you have determine which one is your central atom. Remember, we said that fluorine can never be terminal atom. I can never be central atom. So nitrogen, and nitrogen has a lower electronegativity than fluorine. So N is placed at the center, and you surround it by the 3 fluorine atoms. Then you sum your, we can do this first, sum your total number of valence electrons. Nitrogen is in group 5, and we have 1 atom of nitrogen, that is 5 electrons. Fluorine is in group 7, and we have 3 of them, 3 times 7. So you have 26 valence electrons. Total number of valence electrons is 26. So what we do now from the rule, it says that we should give the electron pairs to our make every one of them an octet. So let's start from the central atom. So we have the terminal atom, sorry. Fluorine is already 1, 2, 3, 4, 5, 6, 7, 8. The other fluorine, 1, 2. So we have 1, 2. These are the bonded ones. 3, 4, 5, 6, 7, 8. So this is another octet. Let's add this other fluorine. 1, 2, 3, 4, 5, 6, 7, 8. So all our terminal atoms are now happy because they are octets. So now, but let's count all the electrons that we have so far. So we have 1, 2, 8, 8, 8. 8 times 3, that's what? 24. Now, but the total number of electrons that we have is what? 26. And we've only been able to assign 24. So the rule says that the remaining electrons that are left, we give them as lone pair of electron on the central atom. So the remaining 2 now, we now give nitrogen, because if you look at nitrogen, nitrogen is not happy. Because if you look at this, let me erase this. Nitrogen is, you can see nitrogen is 1, 2, 3, 4, 5. Oh, sorry, and eraser. Let me erase this. So if you look at nitrogen, fluorine is happy 1, 2, 3, 4, 5, 6, 7, 8. This other fluorine is happy 1, 2, 3, 4, 5, 6, 7, 8. This other fluorine is happy 1, 2, 3, 4, 5, 6, 7, 8. But let's count for nitrogen. 1, 2, 3, 4, 5, 6. Nitrogen is not happy. And the rule says that they must be octets. But if you count all the electrons we have so far for the terminal atoms, they are 24. But the total number of electrons is 26. So the rule says that if you have extra electrons that have not been used, we'll give our central atom. And when we give these 2 to nitrogen, nitrogen is now happy. Let's count for nitrogen at 1, 2, 3, 4, 5, 6, 7, 8. So that is how we now have a lone pair of electrons on nitrogen. This is the Lewis structure for nitrogen. Yes, somebody is raising hand. Okay, let's look at another example. So this is CCl2F2. CCl2F2. The least electronegative element here is carbon. How nitrogen got the lone pair? I've already explained before. But nitrogen got the lone pair. The reason why nitrogen has a lone pair is that by the time the rule, if you look at the rule, let's go back to the rule. The rule says that determine the total number of valence electrons, which we did. So let's look at the rule. The rule says determine the total number of valence electrons, and for NF3, nitrogen has 5, fluorine has 7 times 3, that's 21 plus 5, 26 valence electrons. And the rule says that we should determine the atom connectivity. And it says place electron pair around terminal atoms so that each terminal atom has an octet. So that was what we did. We put the electron around the terminal atom. We gave each of them a pair, 1, 2, 3, 4, 5, 6, 7, 8. You have to count this one as well. For this to 1, 2, 3, 4, 5, 6, 7, 7, 8. For this also 1, 2, 3, 4, 5, 6, 7, 8. That's what the rule says. It now says later that any remaining electron will be given as lone pair to the central atom. By the time we give all the terminal atoms 8 electrons, 8 times 3 is 24. We have total of 26. So the remaining two is given to nitrogen as a lone pair of electron. Who are these writing names now? I've told you don't write any name. I don't want to see any name and matric number. Simple instruction you don't listen to. So now we have another one. We have CCl2F2. So carbon is the least electronegative element. So it will be the central atom. As you can see, carbon, we now surrounded by 2 chlorine and 2 fluorine because these are the terminal atoms. So in calculating the total number of valence electrons, so the total number of valence electrons, calculating that we have 32 valence electrons. 4 plus 7 times 4, that's 28 plus 4, that's 32. And the rule says that we should give each of these terminal atoms, we should make them octets. So chlorine will be 1, 2, 3, and give them in pairs 4, 5, 6, and you see now the 7, 8. Let me erase this. So that is 7, 8. This also 1, 2, 3, 4, 5, 6, 7, 8. This also 1, 2, 3, 4, 5, 6. Oops. 1, 2, 3, 4, 5, 6, 7, 8. This other one 1, 2, 3, 4, 5, 6, 7, 8. These ones can be joined together to form a bond. So this is a bond. Now you can see here now. The bond is here. There's a bond here already. There's a bond here already. So now all our valence electrons, our valence atoms are happy because they are all 8, 8, 8, 8. So now when you count 8 times 4, 32. Our total number of valence electrons is what? 32. So meaning that we are happy, there's no lone pair of electron on carbon. Now let's look at carbon also. Is carbon happy? 1, 2, 3, 4, 5, 6, 7, 8. Carbon is also happy. The valence electrons are happy, and that is the Lewis structure for that particular compound. So there are times that you could have more than one central atom. Sorry, I lost my screen. So there are times you could also have more than one central atom. Let me go back to my slide. So you could have more than one central atom, as in the case of this compound, CH4O. CH4O, that is CH3OH. And so now we know that carbon and oxygen are the central atoms. So you also calculate the total number of valence electrons. You will calculate this to be 14. Hydrogen has that 1 times 4. 4 hydrogen, 1 carbon atom times 4. Oxygen is 1 times 6. That's 14 valence electrons. So I know that your hydrogen can never be an octet. So in this case now, your hydrogen has 1, 2. The other hydrogen has 1, 2. The other hydrogen has 1, 2. And this also has 1, 2. This other one has 1, 2. So these are 8 electrons. break. So if you count this now, we have for carbon, each of the hydrogen is a duplex, 1, 2, 3, 4, 5, 6, 7, 8. I know that we have 14. So the remaining 6 electrons will not, the remaining 1, 2, 3, 4, that's 8. Then you count this one, this is 9, this is 10. So you have 10 electrons that have been given, remaining 4. So these 4 electrons, but if you look at oxygen, oxygen is always just having 1, 2, 3, 4. So the remaining 4 electrons will give oxygen as a lone pair of electron. And now we now count for oxygen now. Oxygen now has an octet, which is 1, 2, 3, 4, 5, 6, 7, 8. This carbon is also a octet, 1, 2, 3, 4, 5, 6, 7, 8. And the hydrogen are duplets, 1, 2, 1, 2, 1, 2, 1, 2. And all the 14 valence electrons are fully taken care of. So let's look at multiple bonds. Sometimes, if there are not enough electrons for the central atom to attain an octet, that means that a multiple bond will occur. So far, the one we've looked at as single bonds, there could be multiple bonds. So if the central atom does not have a full octet, change a lone pair on the surrounding atom to another bonding pair to the central atom. So we'll give an example for that. An example for that is your C2H4. So C2H4, let's look at the rules. For C2H4, your central atom so if you look at C2H4, which one is the central atom there in C2H4? Which one is the central atom? Which one is the central atom? Yes, carbon is the central atom. And we have 2 carbon atoms. So we can write the 2 carbon atoms as this, C and C, surrounded by 4 hydrogen atoms. 1, 2. And you want them to be mirror images of one another. There's another hydrogen atom here, another hydrogen atom here. So let's look at, so let's connect them together. So this connects to 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 this. So now, what is the total number of valence electrons that we have? The total number of valence electrons. The total number of valence electrons. Calculate the total number of valence electrons. Yes, we have 12 valence electrons. The 2 carbon atoms, 4 times 2, 8, 4 hydrogen atoms plus 4. That's, thank you. So now we need to put the electrons around the valence atoms. Do you need to put anything there? Hydrogen is already okay, 1 bond. So this is 1 electron here, 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 1 electron here. So how many electrons have we assigned now? So this is 1, 2, 3, 4, 5, 6, 7, 8. Then we count this one, 9, 10. 10 electrons, thank you. So we have 2 electrons left. We have 2 electrons left. What do we now do to these 2 electrons? We can't put one there, and the rule says we should give it, if we put the 2 electrons here, this carbon will be happy. Let's count for this carbon. 1, 2, 3, 4, 5, 6, 7, 8. This carbon is happy. Let's look at this carbon. 1, 2, 3, 4, 5, 6. This is not happy. This is happy. So what do we do? The rule says that if we still have insufficient electrons on one of the central atoms, We will now migrate this lone pair and bring it between the two of them. So we put the lone pair here. So this will now become carbon, double bond, carbon, and your two hydrogen atoms, 1, 2. The other carbon atom, 1, 2. So now we can see that if you count all the valence electrons, they will be very happy. Let's see. Hydrogen has 1, 2, 1, 2 duplets, 1, 2 duplets, 1, 2 duplets. Let's count for this carbon. 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is happy. Let's count for this too. 1, 2, 3, 4, 5, 6, 7, 8. So that is how you form your when you have insufficient ones. That is for C2H4. So that's the example that has been done here. So you see this lone pair of electron, what we simply did was we migrated it from here, we brought it here. And when we brought it there, a double bond came in. So there's no lone pair again. The two of them are sharing the lone pair of electron. And in sharing them, they are both happy. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That is how we do for that. Let's look at the second example, which is the second example is nitrogen. Nitrogen has 10 valence electrons. So maybe I should not even draw it yet. So we have nitrogen, and we have 2 atoms of nitrogen. So nitrogen, nitrogen. So how many valence? This one has 5, this has 5. So I have 5, you have 10 valence electrons. And the rule says we should give each of them a duplet 1. So there's a bond between them already. 1, 2, 3, 4, 5, 6. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 electrons. When we look at these 10 electrons, this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen is happy. His other nitrogen friend, 1, 2, 3, 4. This is not an octet, it's not happy. So what do? We migrate this electron, we bring it here, this pair, we bring it here. We take this also, we bring it here. So at the end of the day, what do you now have? Now have nitrogen, 1. I know that nitrogen can have 3 bonds. So the other nitrogen is there. And the lone pair of electrons are on each of them. So when you count, you have 1, 2, 3, 4, 5, 6, 7, 8. If you count for this also, 1, 2, 3, 4, 5, 6, 7, 8. That is how we get double bonds in our Lewis structure. So the double bonds is usually as a result of when the octet, so in this case now, we migrated them here and the two of them have lone pairs of electrons. So that is the end of the class. Sorry that our time is fast spent and the class is coming to an end. So see you next week by the grace of God.